The ordinary least squares estimates of the slope and the intercept, we've looked at those formulas before, and they're pretty simple. They look a little complicated, but they're really derived from very simple things that we can calculate from the data. So for example, the slope estimate formula, beta 1 hat, that's the estimate of the slope, is the ratio of two things. It's the sum of the deviation of x from its mean times the deviation of y from its mean in the sample, added up over all the observations, and then we take that whole thing and divide it by the sum over all observations of the deviation of x from its mean squared. And it can be shown, we won't do it here, that this is the equivalent of this nice ratio. That is, that the estimate of the slope is the ratio of the sample covariance of x and y to the variance of x. So that's the slope estimate. The intercept estimate is a very simple formula. Once you know beta 1 hat from the preceding formula, we just take the sample mean of y, we subtract out beta 1 hat times the sample mean of x, x bar, and that leaves us with our estimate of the intercept term, beta 0 hat. So those are fairly straightforward. The computer calculates this all very easily, but where did these formulas come from? So we're going to take a look today very quickly at the derivation of the ordinary least squares values of the intercept and the slope. And as you may recall, the objective here is to choose those values, b0 and b1, such that they minimize the sum of squared errors or prediction mistakes in our sample. Now, what is the prediction mistake? The prediction mistake is yi minus yi hat, where yi hat is the value of y that's predicted using our regression line. So it looks something like that. And it's just the intercept estimate plus the slope times the particular value of x for that observation. That's yi hat. Now that may or may not be on target. Typically it's not exactly right, and so there's going to be some difference here between the actual value y and the predicted value y hat. We take those deviations or mistakes, square them, and add them up over all n observations in the sample. And so hence that's what that is. And if we take this formula and substitute it in for y hat, we get this alternative, and this is the thing that we're going to take and try to minimize. And we need to choose the values of b0, the intercept, and b1, the slope, to make that overall sum as small as possible. Now, you know how to do this because you've taken calculus, and to find the minimum of something, we want to presume that it has a shape something like this. And we want to go to the bottom. So what's true at the bottom is that the derivative is 0, of course. Now it could also be a maximum, but in this case it is going to be a minimum. So to derive this mathematically, we're going to take the first derivatives with respect to each of these coefficients, b0 and b1, and we're going to set those derivatives equal to 0. So let's see what those derivatives look like. They look a little complicated, but they're really pretty straightforward. So since these are partial derivatives, we've got more than one variable we're taking a derivative with respect to. We use the partial derivative. That's what that means. And here was our formula for the sum of squared prediction errors that we had from the previous slide. And now we can, since this is a sum, and notice I've suppressed the I equals 1 to n just to keep the graph, the picture less cluttered. So we've got this big sum. But remember, sum is just, a whole string of things added together. And so when we take a derivative, we can always, the derivative of a sum is always the sum of the derivative. So I've just taken the derivative inside here, right there, and then we've got this formula, this expression in the brackets. Now, how to deal with this with a derivative? We're going to employ two familiar rules of derivatives. First is just simply the power rule. So here we have a whole expression raised to the 2 power. We're going to take the 2 down in front and subtract 1 from it, and that leaves us this part right here. Right? Within the sum. 2 times the thing in parentheses. But we also have to apply the chain rule, and that is because the thing we're taking the derivative with respect to, b0, is inside those parentheses, and it has that little negative in front of it. So we have to take the derivative of b0 with respect to b0 inside that parentheses and multiply that on. That's the chain rule. So that's what gives us that little -1 here, tailed onto the end there. And that negative 1 times 2 is negative 2. We can take that outside the sum, so that came out here, and we're left with this expression, which is the first order condition, technically speaking, for this minimization problem. So this is our first condition. This is the whole derivative condition, which we set equal to 0 for B0, the intercept term, and that would be true at the minimum. All right, that's step 1. Now, step 2, we have to do the same thing, the derivative with respect to B1. I'm not going to drag you through all the steps, but you can see them here pretty clearly. We're doing pretty much the same thing. We take the derivative inside the sum, and we're taking it with respect to B1 in this case. But again, we're going to use the power rule because we have something in parentheses raised to the 2 power, so the 2 goes out in front. And then the chain rule here, notice that B1 is multiplied in this case by negative xi. So we have to bring the negative xi out according to the chain rule, taking the derivative inside the parentheses. Factoring out the negative 2, we're left with this expression here, which also has to be true when we minimize the sum of squares. So we had the preceding and this present condition are our first order conditions for the minimum. Now, what's that? Well, we have 2 equations, which we just derived, and we have 2 unknowns, and those are B0 and B1. So that's just algebra, right? Solve those 2 equations in 2 unknowns. They do have a solution. Now, to make things a little bit simpler as we go along, I'm going to note a couple of things from the start. These are just little first steps. First of all, notice, recall the definition of the sample mean, x bar, right? It's just you add up all the x's and divide by n, and we can solve that to get that the sum of xi is equal to n times x bar. That's going to be useful in a minute. And by the same token, the sum of yi is always equal to n times y bar. Now here's another little thing which is a little bit messier, but it's also going to be helpful at the end of the derivation. If you have an expression like this, the sum of x minus x bar quantity squared, you'll notice that was, if you may recall, that was in the denominator of the slope estimate. We can expand that thing that's in parentheses squared to this. All right, that's just simply expanding the square, and then we can distribute the summation term here, here, and here. And just collecting a few terms and using the definition that we had back here, it ends up that this ends up being equal to this thing here. So this is equal to that. And that'll also turn out to be handy as we move through the derivation. Alright, now we're just going to get working. And you can read through the steps yourself. I'll walk through them pretty quickly. So let's take the first derivative formulas, and I'm going to start with the one that was the first derivative for B0, right? And that looked like this. Well, the negative 2, we can divide both sides by negative 2, and that just cancels out because it's equal to 0, so we're left with this second thing here, right? And then I'm going to distribute the summation across the different terms there that we can do as well, because everything's just being added up. And then here, we're taking advantage of that thing that I just showed in the previous slide, right? That the sum of y is equal to n times y bar. Here, this step is taking advantage of the fact that B0 is just a constant term, so when you add up n constant terms, you get n times B0. And we're kind of applying both things here to take this step. So we move from there to there, using a few of those tricks, and we divide both sides by n. And you're left with this thing, and this is really the punchline, although let's use a different color. This is really the bottom line, right? Now, here I've solved for B0, so B0 from this preceding equation is equal to this, y bar minus B1 x bar. But we're going to call it beta 0 hat, because that's the one that is the ordinary least squares estimate. Okay? And as you'll probably note in class, this little formula implies that the ordinary least squares line passes right through the means of the data, x bar and y bar, which is a nice property of ordinary least squares. It really slices right through the center of the data, if you like. Now, the other derivative, which is with respect to b1, there's a lot of steps here, and there's nothing that's very complicated, but it's a bit tedious. But here's what we started with, was this guy right here. Again, we divide through by -2, so we simplify it a little bit to get to here. We distribute the summation across those different terms here. And then to get to this step, this took advantage of what we just derived. Namely, I took the B0 formula that I had just found in the previous slide and substituted it in, right? So y bar minus b1 x bar right there is b0. And so now, if you look at this line here, the fourth line in my derivation, everything is in terms of b1. So at this point, it's just a matter of cranking it out and solving for b1. And you'll notice I did a couple of other little steps here, like this here. I took advantage of the fact that the sum of xi is equal to n times x bar. Alright, so now I distribute that y minus b1 x bar, and I end up with this little term, this equation here. Still, it's all equal to 0. And then going to this next equation, what I've done is I've moved the b1 part over to the other side. Right? So now we've got that the sum of xi yi minus n times x bar y bar is equal to b1, and all the b1s are over there. I factor out the b1, and I'm left with this. Now, I didn't quite show a step here, but this took advantage of a previous derivation at the very beginning, which was that the sum of xi minus x bar quantity squared can be shown to be equal to the sum of xi squared minus nx bar. Right? That was something we showed toward the beginning. And finally, when you pick it all apart, you're going to end up with solving for this. I divided through by that sum of x minus x bar squared, and that leaves us with this expression, and that's exactly what the OLS estimate of the slope is, and I call it beta 1 hat. So now we've got beta 1 hat, we've got beta 0 hat. Now if you've been paying attention, you see that I didn't explain something I did, which was this move right here. And that relies on something very similar to this business right here, and I didn't bother trying to show that to you, but you could easily show that to yourself, that those two things are equivalent to each other, and that gets you to the final result. And so, in spite of the fact that it seems tricky to minimize the sum of squared deviations and find the B0 and B1 that do that, it turns out to be, with a little bit of calculus and algebra, really fairly straightforward and super easy for the computer to do. And that is the derivation of the ordinary least squares regression coefficients.